Alkyl halides, also known as haloalkanes, are organic compounds in which the carbon atom of an alkyl group is attached to a group 17 element, one of the halogens, fluorine, chlorine, bromine, or iodine. Alkyl halides can be classified as primary, secondary, or tertiary, depending on how many carbon atoms are attached to the carbon that bears the halogen. So the alkyl chloride on the left of the screen here is primary, the alkyl bromide in the middle is secondary, and the alkyl iodide at the right, in which there are 3 carbon-carbon bonds attached to the carbon that also bears the iodine, is tertiary. This maps directly to what we already know about alcohols, where the terms primary, secondary, and tertiary are used in a similar way to reflect the number of carbons attached to the carbon that bears the OH. But remember that we use these terms slightly differently for amines, where primary, secondary, and tertiary relate to the number of carbons attached to the nitrogen of the amine. When it comes to the reactivity of alkyl halides, the key factor at play is electronegativity. Remember that carbon has mid-range electronegativity at about 2.5. Now fluorine, chlorine, bromine, and iodine are all more electronegative than carbon. This means that carbon-halogen bonds are polarized, as shown here for a carbon-bromine bond, with a partial positive charge, shown as delta plus on the carbon, and a partial negative charge, or delta minus, on the halogen atom. This polarization is key to how alkyl halides react. There are 2 main reactions of alkyl halides that we need to consider for now. Both involve breaking the carbon-halogen bond. The first is a substitution reaction, in which the halide, bromide in the example shown, is replaced by an incoming nucleophile. Because cyanide, or Cn-, and bromide, Br-, are both nucleophiles, we call this a nucleophilic substitution reaction. One nucleophile takes the place of another, sometimes abbreviated capital S subscript capital N. In the second reaction pathway, the halide leaves the organic molecule along with a proton, H+, from the carbon next door. This forms an alkene product and is an elimination reaction overall, abbreviated with the capital letter E. Let's look a little more closely at the substitution reaction. For this reaction to take place, 2 things need to happen. The carbon-bromine bond has to break, and a new bond needs to form between that same carbon atom and the incoming nucleophile, cyanide or Cn- in this particular example. In some situations, the carbon-bromine bond breaks first, then the new carbon-Cn bond forms a little later on. For reasons to do with the kinetics of the reaction, which we will discuss more in class, this type of reaction is classified as SN1. In other cases, the bond breaking and bond forming steps occur at about the same time. Reaction via this pathway is called SN2, which we'll also discuss a bit more in class. Looking more closely at the elimination reaction now, 2 things need to happen here as well. The carbon-bromine bond needs to break, and a CH bond from the carbon next door is also broken. Once again, there are 2 main pathways by which this can occur. If the CBr bond breaks first, and then the CH bond a bit later, the reaction is classified as an E1. If the 2 bonds break at the same time, It's an E2 reaction mechanism. These names are linked to the kinetics of these reactions again, and we'll talk a bit more about both in class. There you have it, a brief introduction to the chemistry of alkyl halides or haloalkanes, simple organic derivatives of the halogens fluorine, chlorine, bromine and iodine, and their key reaction pathways: substitution on the left, elimination on the right.